And to a certain extent, it's not really a rhetorical question, because we talk about computer and we bandy around that term a lot in modern culture, but really what is a computer? Well, if you look it up in the dictionary, it says a device that computes. And, that's not really very helpful. It's kind of like using the word to define itself. Especially a programmable electronic machine that performs high-speed mathematical or logical operations, or that assembles, stores, correlates, or otherwise processes information. You look at that definition, and it's basically it takes something that really isn't all that complicated and makes it sound really kind of confusing. So if a computer is something that computes, we need to figure out then what is a computation. And you look up computation in the dictionary, and it says the act or process of computing, and you have this nice circular reference where computer references computing, and computing references computer. So, yeah, it doesn't really help. Here's another definition of computing to determine by use of a computer. Determined by mathematics, especially by numerical methods. For example, to compute the tax due, and of course, most of us are going to be paying taxes in a couple months. Here's another definition that I particularly like. The act of taking a problem with specific inputs and determining a specific answer or outputs. One of the problems that we did before was gas mileage. How energy efficient is your automobile? The inputs we took there is how many miles your car traveled, how many gallons of gas it used to travel X number of miles. Those are the inputs. It then did some computation of it, divided one number by the other, and printed out some outputs. So here, the definition for computing takes some values or inputs, do something to it, and produce some sort of output. A properly functioning computer will always, always, always produce the exact same results for the exact same input. That is a definition of a computer. Given a certain fixed amount of input, it will always produce the same output. And you may look at this and not believe it because, you boot up Windows and half the time it crashes, the other half the time it doesn't. But believe it or not, a properly functioning computer will always produce the same output for the same input. Which, of course, brings up the question, how do we compute random numbers? Because every time we want a random number, we want a different one. We're going to get to that later in the semester. So the first computers. Who knows or who can think of what the first computer was? Anybody?
The abacus.
Abacus, good. Other first computers? If no one raises their hands, I'll pick a random name out of the roster. Come on. Who can think of another first computer? Yes? Calculator, good. Brain? Ooh, that's a good one. I hadn't thought of that. I like that. Other ideas for first computers? Okay. So I had actually, certainly there are biological computers, the brain being one, and using other biological organisms as well. In terms of man-made computers, and I think next time I teach this class I'll probably specify that, one could argue that scales were the first computers. Again, a computer takes inputs and produces outputs. Here it takes inputs such as, all right, how many people saw Monty Python and the Holy Grail? Okay. It takes in a witch and a duck, and it weighs them to see which is heavier. So the input is whatever in scale pan number 1 and scale pan number 2. The output is, are they equal, one's heavier, or the other's heavier? Technically a computer, although a very mechanical and somewhat primitive computer. The abacus, as was mentioned, is also a computer. They was used in, we tend to think of them as Chinese, but there's a lot of cultures that actually use the abacus. They could do very advanced mathematical computations, considering that thing had been around for thousands of years. You can even do square roots on an abacus. So that's also a computer. It takes an input, which is the movement of the beads, and produces some output, which, if you read it through properly, is a series of numbers. Stonehenge is a computer. The way Stonehenge is situated, if you stand right in the middle on the solstice, which is generally June 21st, right around sunset, you're going to stand basically in the middle, and there's a little sort of bowl-shaped rock formation, and the sun will sit exactly in that spot on the solstice. So technically, that is computing whether or not it's the summer solstice. It's a bit of a stretch, but you get the idea. Here the input is the position of the sun, and the output is it summer solstice? Is it not summer solstice? So, of course, during the summer solstice, everyone wants to go and party at Stonehenge, and everybody wants to be in that spot. And you have this big crowd of people that's all kind of shoving in to stand in that one spot. It really does work. You just have a problem of everybody showing up and then graffitiing it. There were many, and you could certainly talk about many other sort of first computers. The widely accepted first digital computer was ENIAC. This was created at the University of Pennsylvania in the mid-1940s, and it was created to compute artillery tables. If you are doing artillery, which is indirect fire, which means instead of aiming at a target, you aim up, and it shoots up in a nice parabola, for those who remember calculus, and lands ideally on your target. But depending on the weight of the payload and wind conditions and how far it is to where you're going and humidity, there's a lot of angles that you have to compute to actually get it to land on your target. And these were done by people with, computing this stuff by hand. So the Department of Defense said, all right, let's create a big magical machine that does that, hence ENIAC. Electronic Numerical Integrator and Calculator is what it stood for. And you could literally drive a school bus into this thing. It was so huge. Here we have an individual operating it, and you just see how big this room is. 50 years later, on the anniversary of ENIAC, which was the mid-1990s, they hold on while I choke. They took ENIAC and they reduced it to a microchip. And this ENIAC being, you could fit a school bus inside. The new ENIAC was the size of your little fingernail. And I just find this particularly interesting because they took something so huge, and in 50 years, they were able to replicate the exact same thing on a chip that's basically the size of your fingernail. And especially with the advent of nanotechnology, it's going to get much smaller in the near future. So, okay, we have a computer. Well, actually, I want to back up a second. There are many other first computers. My first computer was a Commodore 64, which probably I'm dating myself. IBM came out with the PC which actually wasn't the first one to come out with the PC, but they came out with the PC in the late 70s, early 80s. That was sort of the first home computer. Macs came out around that time as well. And essentially, ever since then, they've been getting bigger, better, faster, and smaller. Yes, they've been getting both bigger and smaller. You know what I mean, even if I'm sticking my foot in my mouth here. So we have a computer. Great. We have a PC that we bought, a Mac that we bought, a hand calculator, what have you. What do we do with it? And so somehow we need to tell it what to do. And in particular, we need to give it some sort of directions. Now, computers are dumb. They have zero intelligence of their own. Contrary to most science fiction movies, they don't really talk back to you and can't make decisions other than those things that the humans explicitly told them how to figure out. They have zero intelligence. So we are going to tell a computer what to do by writing a computer program or an algorithm. An algorithm is just a set of directions. That's all an algorithm is. So in this course, for writing it in a computer, we're going to use the Java programming language. And we're going to take some set of directions or an algorithm and translate that into Java, and then the computer is going to go and make it work. And the purpose of this course is both to be able to develop the algorithm, meaning how it's going to work, and translating it into Java. So, what's an algorithm? The definition in the dictionary says a step-by-step problem-solving procedure, especially an established recursive computational procedure for solving a problem in a finite number of steps. Right, that's from the online dictionary. So we've seen lots of algorithms before. In particular, Google Maps or Google Directions. This here is the directions for how to get from the computer science building, which is right by the stadium, to the Buddhist Biker Bar and Grill. It's a restaurant. And obviously, we have a set of directions. Here are the 5 steps of the directions. Head in a certain direction on a street, go this certain distance, turn. Head another direction, so we bear right, we go, well, 0, that's bad. Turn left on Jefferson Park Avenue, go 0.6 miles, turn hard left on West Main Street, et cetera, et cetera. Here is a specific algorithm how to accomplish something, in particular how to get from point A to point B. When I had to replace my car radio, I ordered it through, I think it was Crutchfield, and they sent me these directions, which really works for me because I have no idea how a car works. The vertical pedal goes, the horizontal pedal stops, that's about it. So this here are the directions or the algorithm for how to remove half of my dashboard so that I could replace my car radio. Recipes. These are algorithms. So from the Moosewood cookbook, we have risotto with carrots and feta. And again, we have a series of steps. Get all your ingredients, and then the steps, and this is written it doesn't list them numerically, but this paragraph essentially is telling you all the steps. The thing to be done with this algorithm is given your input, which is your ingredients, produce your output, which is your meal. Okay, questions so far? We good with algorithms? How many people would agree with me that those two colors are the same? Or if not exactly the same, they're really, really, really close? All right, how many people would agree with me on that? Does anyone disagree with me on that? Okay, you think they're different? Okay. So I'm going to turn out the lights for a second. This bar is it's the same shade, and I think we could agree that if there is a color change, or we would agree that if there is a color change, it's not much. Does that sound feasible? Okay. Those were spots A and B. I'll go back. So here, can I do these both? There we go. And then here. So the reason this works, this particular optical illusion, and this is actually one I particularly like, the human eye, because this one is surrounded by really light stuff like, light gray and white, it looks much darker because of the contrast. This one, although it's the same color, because it's surrounded by really dark stuff, it looks lighter. And you might not believe this. I didn't. I literally opened this up in Photoshop and did color chooser and found the color of this square and the color of this square. Really, they're the same. And you're welcome to download these slides and actually do that as well. But these are actually the same color. Right, and that's that same bar there. You notice now it looks like it's a gradient, like it goes from a dark color to a light color. Okay, so we now have a rough idea of what an algorithm is. But it turns out that not all algorithms are good. And I have good in quotes because the question is, of course, well, what makes a not good algorithm? Or what makes an algorithm bad? Well, there's a number of problems that we can have for a bad algorithm. It can just be plain wrong. It can be very inefficient. It can never stop. It means it just goes on and on forever. And there are other problems. These three are the ones that we're going to see in the next couple slides. This is an example of an incorrect algorithm. And you'll notice here that the road curves to the left, the sign curves to the right. I think we can all agree that that algorithm is just wrong, unless you're going into the driveway, but I don't think that's what the sign... I don't think you could be going 40 kilometers per hour into a driveway. So MapQuest directions. If we wanted to get from point A, consider directions to get around grounds. Point A to point B on grounds. Again, this is computer science department to, I don't know, what's that, the hospital? Yes, it looks like the hospital. This is a correct algorithm from getting from the CS department to the hospital. This is also an algorithm for going to the CS department to the hospital. Notice you take a bit of a tour around the United States to Seattle and Los Angeles and back. This is not an incorrect algorithm. This will get you from point A to point B. Granted, it'll take you about 8,000 miles to do so, but it will get you from these. So this is not an incorrect algorithm. It's just an inefficient algorithm. And when we look at this, this is obviously not what we want in MapQuest directions. We want the shortest path. however you define shortest path, but this is obviously not what we're looking for. So you take shampoo, and if you look on the back of shampoo, one of the more interesting directions there, it says gently massage into wet hair, lather, rinse, and repeat. Does anyone see a problem with this? Lather, rinse, repeat. Lather, rinse, repeat. Lather, rinse, repeat. As it turns out, this used to be the big joke among computer scientists that, joke. I mean, I'm sort of using this I mean, it's not really a joke, but this was known among computer scientists and talked about in courses like this because all shampoo bottles said this. So when I was actually preparing this lecture, I think for last semester, I went into CVS. I spent like a half hour there looking at the back of every shampoo bottle, and none of them say it anymore. And I was so disappointed because I was going to buy whatever shampoo bottle did it so I could take a picture. So it really says lather and rinse, repeat if desired. So only if you desire it would you be stuck forever. So even though this particular version of shampoo doesn't say lather, rinse, repeat, many of them did years ago. I just unfortunately don't have one. So this algorithm repeats forever. In particular, this algorithm never halts, meaning it never stops. Lather, rinse, repeat, lather, rinse, repeat. We're going to talk about algorithms halting in a bit later on in this semester because it's actually a bit of a problem. How do you know if a computer program will ever halt? Maybe it will go on forever. Can you tell that ahead of time? So humans, obviously, given the directions lather, rinse, repeat, are not going to be stuck in the shower forever. A human has intelligence. A human knows that at some point you have to stop. Maybe when you run out of water, or you run out of shampoo, or you fall asleep. Computers don't know this. Remember, computers are dumb. They have no idea that you shouldn't go on forever. If you were to tell this to a robot that has no intelligence, it would sit there lathering its hair forever and ever until it stopped working. So we need to be very explicit in how we tell a computer what to do, because if we mess up, it will, for example, go on forever. So this is a very overplayed and actually not very funny computer scientist joke. How did the computer scientist die in the shower? Okay, ready for the punchline. She read the directions, lather, rinse, repeat. No, it's really not very funny, but at least now you get the joke. Ha ha. Okay, back to the cookbook. Golden cheddar cheese soup. If you look at this particular algorithm, salt to taste, minced fresh scallions, chives, or parsley. This algorithm is not exact because it does not do exact step-by-steps to get it done, because it tells you add salt to taste. Well, maybe I like it salty and you like it less salty. Or maybe I hate scallions and you like parsley. So how this algorithm actually works is not clearly specified. Again, a human doesn't have a problem with this because a human can say, oh, sure, I like lots of salt. I'm going to add the whole can of it. Or can say, I'd like only a little bit of parsley because I don't really like it much. A computer can't figure that out. So consider this algorithm, which is supposed to have a nice animation, but doesn't. So let's say we're given some integer n. We're going to keep track of a running sum. So essentially what happens is that, let's say we start with 5. We're going to keep track of an ongoing sum, which starts at 0. Right? So what we do is we have our sum, we have our n, and we're going to take n, add it to sum, and then subtract 1 from n. It's going to go through again. Take n, add it to sum, subtract 1 from n, et cetera, et cetera. 3 plus 9 is 12, becomes 2. 2 plus 12 is 14, this becomes 1. 1 plus 14 is 15, this becomes 0. Once we're at 0, we stop. So all this is doing is given some number, it's computing the summation of that number down to 0. Right? A fairly short algorithm. Will this algorithm stop? How many people think this algorithm will stop in this case? Okay. How many people think this algorithm will always stop? It's a bit of a trick question. Can anybody think of a way that this algorithm would not stop? So what happens if you start with a negative number? You take the negative number, negative 1. You add that to sum becomes negative 1, it becomes negative 2. Add negative 2 to the sum, and becomes negative 3, then negative 4, then negative 5. This particular algorithm, if given a negative number, would not stop. So here we have an algorithm that anytime we give it a positive number, or possibly 0, it will stop, right? It computes, I mean, it may take forever. You get a million, it's going to take a million steps, but it will compute the sum from that number all the way down to 0. But if you give it a negative number, this algorithm doesn't work. So here we have a situation of an algorithm that generally will figure out what you want it to do, because most people who are going to use this algorithm are going to give it a positive number. But it's certainly possible to make this particular one run forever. It is possible that this algorithm will not halt. Sure, it's possible it will halt, but it's possible if you give it a negative number, it will never halt. So in this case, we could just say if, n is negative, don't do anything, and then it would solve that particular problem. So our goal is to write correct and efficient algorithms for a computer to follow. Now, we're not really going to worry so much about the efficiency in this course. There are many ways to measure computer efficiency. We're going to talk a little bit about it. I'm not so worried that your algorithms be the most efficient possible. So, going back to my series of questions, what does correct mean? Well, what if I said display the color blue? I think we could all agree that this is blue. And I would think we could all agree that that, a bit of a lighter shade, but is also blue. So here we have, we said display the color blue. We have two correct results. Is this blue? Well, that's sort of questionable. I think some might say it's green. Some might say it's blue. I think everybody could agree that that is in between blue and green, wherever it lies on that scale. So maybe that's blue. And I think we could all agree that that is definitely not blue. So here, we are specifying an algorithm, but not very precisely. We've just said, give us the color blue, and we've seen two and a half answers that would qualify. We've seen one answer that definitely wouldn't. So what we need to do, this also is not an incorrect algorithm, it's just an inefficient one. This was the tour of the country to get to the local restaurant. So humans specify algorithms without a lot of precision because human intelligence can add the necessary precision. If you say blue, I can figure out that you probably don't mean blue-green. You probably just mean blue. Go from here to there, a human knows that you mean the shortest path. But a computer can't figure that out. So what we need to do is we need to specify exactly which color to display. Give me the color 0x0000FF. And whatever that means, that happens to be the formal color specification for a saturated royal blue color, which is kind of whitewashed because of the projector. In that case, there's only one possible outcome. There's only one color that matches that numerical specification. Find the shortest path from here to there. Then a computer can figure out. It knows exactly that however you want to get from here to the restaurant, it's not going to route you through Seattle because that is not the shortest path. So the reason I'm going through all of this is we need to keep in mind that we have to be very specific when telling things to a computer. They're very dumb. Questions or comments so far? Okay. So this is, I'm sure many people have seen ice sculptures or various other culinary creations. This is a series of carved watermelons, which some I think are surprisingly impressive. This did appear around the time Lance Armstrong was running his 27th time on the Tour de France. So, who knows kanji and can tell me what those say? Does that say like swan and turtle? Anybody? Oh, happy birthday? Oh, okay. I thought it was like swan, turtle. I know like the numbers in kanji. I think that's about it. And that one? Same thing? Okay. So now the question is, we figured out our algorithm. We know how we want to go about doing something, and now we have to tell a computer to go about doing it. How do we do that? Well, in Star Trek, you say, computer, tea, Earl Grey, hot. And it magically appears because that's how everything happens in Star Trek. And in a lot of movies, whether they be current movies or science fiction future movies, I mean movies about sort of current times or science fiction in the future, computers can understand English. And that doesn't actually work in the real world. And there's lots of reasons to believe that it may never work. So the fact is we can't really tell a computer what to do. Part of the problem is English is so imprecise that if you're trying to tell a computer what to do, it can't really figure out exactly what you mean. Question?
What about devices with voice recognition? Does that have anything to do with computers, or is that something else?
Good question. So the thing was devices for voice recognition. What happens there is you are speaking not in sort of regular English, but a sort of fixed dialect. If you are just narrating for an essay, then sure you can say anything, and it's going to recognize the sounds that your mouth makes and translate that or transliterate that into text. But if you want to actually navigate a computer, you say file, open, file, print, and you sort of have to talk very slowly. File, pause, open, pause, file, pause, print, settings, properties, double-sided. And you sort of have to talk that way, telling it, it's going to give you a list of options or a list of buttons. You tell it exactly which ones you want it to press. So that's not really so much understanding. I mean, here, maybe I should use a different terminology. The difference between understanding English and comprehending English. So there, that understands English. It takes the sounds you make and translates that into computer commands, but it doesn't comprehend the meaning of it. It just knows if you say file, I'm going to open the file menu. If you say print, I'm going to open the print menu. But you're given a very limited subset of tasks, and you can't just say, hey, computer, would you please print this document? Or please print this for me. Or I'd like this to be printed. To a human, I've said the same thing in 3 different ways, but a computer is not going to know because you didn't say file, print, document. So that's essentially voice recognition. It can understand English in that it translates it into text, and then it can do something with that text, but it doesn't really understand the meaning of it. It just knows that, half a dozen commands will do something. Good question. Right, computers don't understand English. So programming languages have been around almost as long as computers have been around because we have a computer, but we need to somehow make it do something. So Ada Lovelace in 1833 programmed what's considered to be one of the first mechanical computers. When I say mechanical computers, I mean it's a series of gears and essentially it was motor driven, so somebody would sit there and crank a motor, and it's gears and holes and pistons and various other things. It's not electronic like any of the modern computers from the 1900s or the current century. And Charles Babbage is the one who created the analytical engine, and Ada Lovelace is actually considered to be the first ever computer programmer. ENIAC, of course, in 1945 that I talked about a couple slides ago, that was programmed by plugging in wires. Literally, you would take a wire out of one thing, walk over to another socket, and plug the wire in. If many of you have seen from pictures or movies from the 40s and 50s when they had the telephone operators who would take wires out and plug it in so to connect your call, that was the same basic idea of how to program a computer. Then they made a great improvement, and they were actually able to program in binary. And this, if you imagine, this was actually a huge improvement, 1001000101010. You look at that and you have no idea what it means. I don't know what it means. But you didn't have to walk around plugging wires into sockets all the time. That was a big step, but computers were not going to take off if that's the only way that you could actually program. So they came up with assembly, which again was a huge, big step. Still kind of difficult to use. For those who continue in the CS courses, CS216, you actually go over assembly language. It's lots of fun. Then they came out with Fortran in 1954. For its time, Fortran was an amazing technological breakthrough. It revolutionized computers. It made computers usable. The problem is that over 50 years later, we're still using it. It was great in the 50s. It was good in the 60s, and we're in the next century. So Fortran, you'll hear often scoffed at. It was amazing for its time, and we would not be where we are today without it. It just should have been retired a long time ago. So then there's a whole slew of other programming languages that you may have heard of. BASIC, COBOL, Pascal. In 1972, Dennis Ritchie, who was working in Bell Labs in New Jersey, developed a programming language called C. So-called because they first developed A, then they developed B, then they developed C. And there actually is a D, but no one uses it. The C programming language is actually still used today. And at some point in your time here, if you are majoring in computer science, you will actually program in C. In 1985, Bjorn Straussup came out with C++. Exactly why it's called C++, we're going to see sometime next week. It's sort of an inside joke that's probably not all that funny anymore. And that introduced the concept of objects and object-oriented programming. Java, and Java is also an object-oriented programming, and basically took C++, took everything that worked and kept it, and took everything that didn't work and threw it out. And they took out some good stuff as well, but that's besides the point. So Java sort of has a long lineage going way back. It is very similar to C and C++ in terms of its syntax. The fact that you need a parentheses here, a curly bracket there, that looks almost identical to C and C++. And for those of you who have seen similar programs, you will see similarities. As you get to later computer science courses, you'll get to experience, well, at least C and C++. No one really uses these anymore. Yes?
What Perl thing?
I'm sorry?
What Perl? P-R-L?
Oh, Perl. The question is, what is Perl? There's a lot of languages that have come of age in the last maybe 10 or 15 years, largely due to the advent of the World Wide Web. PHP, Perl, Ruby on Rails, and a lot of other languages like that. Each of them have their pros and their cons. Perl is particularly good for example, dealing with text documents. The submission system that you guys use when you submit files is something I wrote in Perl, and it's 21,000 lines or something obscenely long like that. Perl is very different than any of the languages that are listed here. It's also not a very good language to first learn computer programming because Perl allows you to be really sloppy in your programming. And if you get into those habits early, it's really hard to get out of those habits. So it's generally considered not a very good programming language. But we may actually talk about Perl a bit later on. So a bit of background. Computing units of measure. A bit is either a 1 or a 0. On or off, true or false. It can't be anywhere in between. So this is how computers think. Either there is a bit, either the bit is 1 or the bit is 0. And obviously we want to keep a lot more interesting stuff in there. For example, images, movies, music files. So what we do is we take bits and we put them in groups of 8 and we call them bytes. Bit, by the way, stands for a binary digit. We use a base 10 number system, and a digit is anything 0 through 9. Well, in the binary number system, it's just 0 and 1. So that's what bit stands for, and then byte is just sort of a takeoff on the word bit. So you take 8 bits, you shove them together, poof, you have a byte. Since each bit can have 2 values, and there's 8 of them, there's 2 to the 8th or 256 possibilities for the values you can store in a byte. And at least now we can store a bit more information than just 0 or 1. We can store anywhere from 0 to 255 or 1 to 256. In particular, 0, 1, 0, 0, 1, 0, 1, 0 equals 74. I'm not so interested that at this point you need to know somehow this magically turns into 74. You don't really need we don't need to go over that for this course, but this is how 74 would be represented inside a computer's memory. A series of bits that are either on or off. So all computing measurements in some way or the other are based on bytes. So we have the normal SI prefixes: meter, kilometer, millimeter, liter, milliliter, what else do we have? Kilogram, et cetera, et cetera. So kilo is 1,000, meg is 1,000,000, gig is 1,000,000,000, tera is 1,000,000,000,000. We've seen all of those at one point or another. So what we computer scientists did is they said, okay, I'm going to make a kilobyte, which is about 1,000 bytes. But computer scientists, for various reasons, instead of making a kilobyte 1,000 bytes, they said a kilobyte is 1,024 bytes because they needed to be different. The reason is that 1,024 works out much better for computing purposes because it's 2 to the 10th. So here, a kilo, the SI, which is the Standards Institute based in Paris, France, defined a kilo as 1,000, and here computer scientists are saying a kilo is 1,024. So they redefined it and said it's called a kibi. And a kibibyte is 1,024 bytes. A mebibyte is 1,024 squared, or whatever that is, gibi and tebi. The difference is that a tebi is a power of 1,024, whereas a tera is a power of 1,000. And they defined this. They had this formal standard, and computer scientists pretty much ignored it. We still call it a megabyte, even though we really mean a mebibyte. We still call it a kilobyte instead of a kibibyte. But these things are actually different. So, and I'm going to get back to why it matters in a second. How much is a byte, or a kilobyte, or a megabyte? Well, if you have an essay, and it's not formatted, meaning you have no bold, no font or colors or anything like that, about 3 pages, a kilobyte is about 3 pages, roughly. If you have a formatted document, you're talking about 5 kilobytes per page. And that's when you have different font colors, different font styles, bold, underlines, different margins. You're talking about 5 kilobytes per page. A digital camera picture, about 1 megabyte each. Depending on the camera you get, it can go down much slower. It can go up to, I think they have 5 and 10 megabyte pictures these days. We're talking about a million bytes for a digital photograph picture. An MP3 music file, it's about a megabyte per minute. So a 5-minute song is about 5 million bytes. If it's on the CD, it's actually 10 times the size, for various reasons we won't get into now. So if it's an MP3, 1 minute is 1 megabyte, or a million bytes. If it's on the CD, 1 minute is 10 million bytes, or 10 megabytes. A movie clip, maybe about 10 megabytes per minute of TV-sized video. Now, the videos that are going to appear on this of this lecture that are being taken are much smaller in terms of the size, so they're actually going to be much smaller than this. So here we have a movie clip. Each minute is about 10 million bytes. So you go out and you buy a hard drive. And a hard drive is where computers store everything. Think of it as like long-term memory. This hard drive, or one just like it, has exactly that many bytes. 250,059,350,016. That is the exact storage capacity of that hard drive, which is 250.06 gigabytes. And here I'm using giga to mean exact powers of 1,000. And 232.89 gigabytes. And here I'm talking about powers of 1,024. So, not surprisingly, when they're marketing this, they're going to say the bigger number because it looks better. You're getting more value for your dollar. So they're going to say this is a 250 gigabyte hard drive. You bring it home, you stick it in your computer, it tells you it's only 233 gigabytes. And you're like, well, where did the other 17 gigabytes go? The thing is that they're using the gigabyte in the proper definition of the term, meaning a giga is 1,000 to the third power. Computer scientists are using giga to mean 1,024. Technically, it's a gigabyte, but again, computer scientists don't really pay attention to that. So this is why whenever you go and buy a hard drive, it looks much bigger in the advertisement than it does in your computer. How am I doing with time? Okay. So, of course, what day would be complete without the demotivators? Agony. Not all pain is gain. Ambition. The journey of 1,000 miles sometimes ends very, very badly. So what I do at the end of the semester is I'll have a vote where everyone gets to vote on their favorite demotivator. And if there's enough interest, I'll then buy them and hang them up in my office. And this one was one of the favorite ones a year or two ago. And well, it was hanging in my office till a week ago when I rearranged my office. But this one either is up or will eventually be up. Apathy. If we don't take care of the customer, maybe they'll stop bugging us. Underachievement. The tallest blade of the grass is first to be cut by the lawnmower. So I will tell you right now that there are some demotivators that are just not going up in my office, period. Not surprisingly, this is probably one of them. I'll tell you which ones were the favorite ones that people voted on, but I don't think some of them are going to hang up there. Have a good weekend. I'll see you all on Monday.